Hello and welcome to the Weekly Space Hangout for Wednesday, February 7th, 2018. I'm Morgan Renberg, and if there's one thing you know about me, it's that I'm not Fraser Kane. I think Fraser and Paul are like swimming in a volcano right now, or whatever you do in Iceland to keep warm. But joining me this week is an amazing panel of astronomers and generally awesome people. As always, we have from EOS Magazine, Dr. Kimberly Cartier. Hey, Kimberly.
Hey, Morgan. I almost said, hey, Fraser. Oh, my God. Hey, Morgan. Happy podcast day.
Happy podcast day to you. From CosmoQuest, we have Dr. Pamela Gay. Hey, Pamela.
Hey, Morgan. Thanks for having me on.
And from the middle of, I think, a blizzard from St. Anselm College is Dr. Nicole Gallucci. Hey, Nicole.
Hi, everyone. Good to see you
Welcome
all again.
back.
Here.
Yes. We've missed you.
I missed you guys too. Yeah, last time you had emailed me, I think I had just started teaching last semester, fall, and I was teaching 2 night labs, Tuesday and Wednesday night. So I was either outside with my students, or more commonly, because this is New Hampshire and not like Arizona, more commonly we were inside playing with simulations and doing some astronomy labs.
So what's new in your life? Do you have any fun projects going on outside of the classroom?
Let's see. Well, the classroom takes up a huge chunk of my time. Outside of the classroom, I am working on, it's not quite, I don't think it's all quite live yet, but the Very Large Array Sky Survey. So the Y-shaped array of antennas in New Mexico is doing an all-sky survey. And I am working on drumming up some blog posts for that. So we'll do some introductory posts. I think there's one already in the queue from one of the lead people in the project. We'll do some intro to radio astronomy stuff, and then we'll get views from the different scientists using the Sky Survey on what they're going to be looking for in this massive treasure trove of data.
So
that's one thing.
How is the Sky Survey going to compare to NVSS and FIRST, which are the previous 2 Sky Surveys that VLA did?
Yeah, so it's going to be, I don't remember the actual order of magnitude or factor, more sensitive than those other surveys. So the Very Large Array has been upgraded with all new receivers, wider bandwidth, so you can see wavelengths of light it couldn't see before. So all of that's going to be a much better increased sensitivity for the array.
Super cool.
Yeah.
Very exciting.
So I do that, and I have there's other stuff. Oh, I'm working on, I don't know which direction Pamela's in, but I'm working on some CosmoQuest user type stuff, motivations, citizen science motivations. And we're still spinning on a grant writing process right now for our college. Lots of little things. Ooh, we just started a diversity program with our physics majors. So yeah, lots of things.
Wow, sounds like you are keeping pretty busy then, and it's understandable that you can't join us.
Yeah, well, now I don't teach labs, so on Wednesday night, so I'm a little bit freer.
Wednesday night lab sounds unfortunate.
It was okay.
And Wednesday night labs. Wow.
Yes.
Yeah.
Yes. It was a lot. Yeah. So for a small college, I had a 50-person astronomy 101 class for a college with less than 2,000 students. Was pretty big.
That's a lot.
Wow.
It's a lot of students.
It's a huge percentage.
Yeah.
Yeah. So it was fun though.
All right. Well, this week we're going to be talking about planets, double dose of planets. We've got the amazing update to TRAPPIST-1, a planet not even in our galaxy. We're going to be talking about some baby asteroids that wandered by planet Earth. But I think there's only one place for us to start this week, and that's with the launch of the Falcon Heavy.
Wait, did something launch this week?
Show of hands, who watched the Falcon Heavy launch live?
For
those of you listening at home, that's 4 hands out of our panel of 4 people.
I joke, but I totally watched. We had a party in our office.
Yeah, I mean, the YouTube stream, I think, had like 2.5 million viewers.
Wow.
And if it was anything like our offices, I imagine each one of those viewers was actually like 10 people crowded around a computer. So I was amazed at the reach that this event got, much less the fact that it basically worked without a hitch.
Just
Musk
about.
had spent weeks talking about.
A little bit.
Yeah.
Almost perfect.
Musk had spent weeks talking about how there's like a 50-50 or a 60-40 chance that it was going to blow up at the launch pad. And then it just leaps off the pad. And I think I've never in my life seen something cooler than the sort of simultaneous landing of the two first stage boosters. That felt like something you wouldn't even believe if it was done in a movie. They were so perfectly timed,
so perfectly synchronized. I mean, like the rockets launched, they separated. It was all very exciting. The car launched is great, and then there was sort of like this minute and a half lag time where it's like, oh, they're floating, oh, they're reaching the landing point, and then all of a sudden the two side by side rockets, they land. They're perfect. They stand. They don't fall over and explode.
Yeah. Well, I hadn't. Oh, go ahead. No, I hadn't been following very close. I unfortunately very unaware of what's going on outside my classroom in the beginning of the semester. So I heard about it on Twitter and I was like, oh, I'm getting back from a committee meeting just in time to see it. And I haven't seen a SpaceX launch in a while. So, like you said, they do all that and then they start coming back. I'm like, oh, these are the ones that land too. I was so excited. Like I actually tweeted my surprise. I forgot about that part. Yeah, I was screaming from my office and my coworker comes in and just kind of leans in. I'm like, rockets, rockets, rockets. But he's a physics professor too, so he gets it.
I think it's incredibly telling that, we can make this comment at the beginning that, well, it didn't exactly work because, the third stage 1 rocket didn't reignite properly and crashed into the ocean at 300 miles an hour. And, we can sit here and sort of chalk that up as a failure when, from 1945 to 2015, literally every rocket that was ever launched crashed back down into Earth. And it tells you that in 3 years, we've gone from, the only way to launch a rocket being to crash it into the ocean to being sort of mildly outraged that they haven't perfectly landed every rocket on their very first try of a new rocket system. I think that's just an amazing development to think how quickly our perceptions and our standards have changed and what that means going forward.
One of the things that really got me was there was a quote along the lines of, you knew it was real because it looked so fake. It was so produced, so shiny, so pretty that Hollywood would have made something more interesting happen as a plot point. And beyond that, it was a lot like what Nicole said. This was something that got so much attention that people who'd kind of forgotten about space tuned back in. One of my favorite things that I read was a older astronomy lover who remembers seeing all of the Apollo launches as a little kid and had gotten kind of, I don't know, meh about what we've been doing with space in recent years, was walking through the food court with his significant other and paused to look at the TV screens and saw the launch and stopped walking when those two returned together, because this was something that reminded us of why we love astronomy, for those of us who sometimes just get so bogged down in the day-to-day details and the budget issues and this and that we forget. And for people who had that spectacular Saturn V moment, or for me, I'm a post-Apollo baby. All of us are post-Apollo babies in this show. For me, I remember seeing the shuttle. And the first time I saw the shuttle coming in, that was my Saturn V moment. And this was the first time I've felt that way since I was 6. And I don't know.
That's a very good point. Yeah, I sort of had those same feelings. And I think anyone who listens to Weekly Space Hangouts regularly knows that I'm not too much into all these, every other week rocket launches. And just the other week I was saying, oh my gosh, what's the big deal with the Falcon Heavy? And I will say, I will eat my words. That was like one of the coolest things that I have seen in astronomy in a very, very, very long time. It was definitely worth the wait. And I will say that I am very glad that center core was not scheduled to land on land, and it was instead scheduled to land on the barge, because if it, missed by a football field and crash at 300 miles an hour, I'm glad it was in the ocean. I will say that.
Yes. Yes.
So did it actually damage the drone ship?
It covered in shrapnel.
It didn't.
Okay.
Yeah, it didn't hit the drone ship, but it blew up like close to the drone ship, and damaged, I think knocked out a couple of its engines.
Better the drone ship than Cape Canaveral?
Yes, absolutely. Yeah. Absolutely.
Isn't that amazing, though, that 2/3 of the engines didn't turn back on. 2 of the 3 engines didn't turn back on. And it still landed close enough to the drone ship that it could damage it.
Yes.
That's amazing. The thing didn't work, and it still basically worked. So what does this mean in your mind about sort of where spaceflight is going, where rocketry is going? What kinds of things do you hope that Falcon Heavy and other sort of large reusable rockets are going to enable in the coming decades?
Cheaper launches for all of the telescopes and satellites that I want to be in space right now. Let's launch them now, please.
What's going to be particularly interesting, and I think here we need the disclaimer of all of us are talking for ourselves and not for any organization that pays us any money.
This is true.
We are all talking for ourselves. I think what's going to be really interesting is seeing what ramifications this has for current development of the Ariane rockets with ESA, with the SLS system, because we're looking at a rocket that was developed for less than $1 billion, if I read the numbers right, is going to be able to launch for less than $1 billion per launch. And it just...
Less than 100 million.
90 million.
Yeah.
So it toasts its competition financially. And what is that going to do to the competition? And are we going to find ourselves torn between, okay, this is the cost-effective way to do it, or because of all of the existing, we've spent so many billions of dollars, are we going to keep going with the SLS systems?
One of the big ways that SLS was sort of sold to the scientific community was that it's kind of, as Kimberly was saying, it's going to open up all of these new opportunities. Things like, direct mission to Uranus without having to do gravitational flybys of Jupiter or Saturn, or putting an orbiter around Pluto, because you can load up an orbiter with enough fuel to slow down and then blast it straight there. That was the justification, the science justification for building the Space Launch System. If Falcon Heavy or New Glenn or its ilk can do that same mission for less than 1/10 as much, and therefore take all that money you save on SLS and spend it to do another science mission, I think the science community is going to get behind these cheaper commercial rockets really quickly, because it could dramatically increase the amount of space telescopes and space missions and experimentation that we can throw up into orbit.
Yeah, for me it was because like Pamela said, we're all post Apollo in this video chat here. I've never seen humans go beyond low Earth orbit in my lifetime, so I would like to see that in more than just video footage. So seeing something not as powerful as the Saturn V, but getting up there again is really exciting. So I don't use space telescopes. I'm a ground-based telescope girl through and through. I don't think my anxiety can handle putting my instrument on a rocket. But from a humanities spaceflight perspective, I have mixed feelings about SpaceX, but they all go out the window when I see a giant rocket go boom. I mean, there's just an emotion there for me. It reminds me of seeing a shuttle launch, for example. You know, Facebook reminded me that it was like 8 years ago I saw one of the shuttle launches. You know, just getting that feeling again is really nice.
So let me ask you. Can I follow up on that, Nicole? Would you rather see NASA buy Falcon Heavies and do a human spaceflight program, or would you rather see these private companies, whether it's SpaceX or another company, sort of doing their own human exploration into low Earth orbit, out of low Earth orbit to other planets?
That's interesting. I guess it depends on how the private companies are proposing to do it. I don't know if they would. I'm speaking completely, off the top of my head here. I don't know a whole lot about space policy, but I would be worried about the safety concerns. I would be worried about not just the safety concerns of the astronauts going up, but the people working on the project on all stages of it. So NASA has a tight control of those things for a reason. Obviously, spaceflight's never 100% safe. I guess let's put it this way. If it was my butt being strapped to a rocket, I'd rather have it be NASA buying the rocket from SpaceX. If it was my personal self on the rocket.
It's a good measuring stick.
So this relates to a question that we have coming in on the chat from Ben Appleby, who asks, why would you launch your payload on anything other than a Falcon? Thoughts?
What else is there?
Well, there's Russia, there's Ariana.
For something distant, I think. What else is up there in that class of thrust?
It hasn't yet been proven that these rockets will. We don't know the reliability of these rockets yet. Mm-hmm. There's no reason to think that the long run reliability of the Falcon 9 will be substantially different than the long run reliability of the Ariane 5 or the Atlas 5. But we don't know yet. And so right now, if you want to be basically guaranteed that you're going to make it into space, then flying on an Atlas 5 or something like that might be a safer bet to make. 5 years from now, 10 years from now, who knows if that'll be true. Or if you want to launch a really small payload. So there's company Rocket Lab down in New Zealand who have a rocket that can launch like 400 kilograms. That's it. Mm-hmm. 400 kilograms. But they're going to do it really cheaply, and it's going to be like your rocket. You're not going to be one of a million CubeSats on a Falcon Heavy launch. And so there might be some operational benefit to having sort of your own private little ride to space, that if you're not one of these mega customers, it wouldn't make sense to buy a $90 million rocket to do.
So when can we do it again?
So there's going to be one more launch in the first half of this year, and it's to launch a communication satellite for Saudi Arabia. And then there should be at least one launch in the second half of this year, which will carry a test payload for the U.S. Air Force. And this is a key step for SpaceX to have this rocket certified to do national security launches. And one of the sort of overlooked aspects of yesterday's launch was that after they reached space, they went on a 6-hour cruise. So basically they coasted for 6 hours, which was much longer than they'd ever coasted the Falcon 9. And that's because it takes about 6 hours to get to the farthest away of the orbits that the U.S. Defense Department classifies as like important for national security. And so this is going to allow SpaceX to demonstrate to somebody who could be one of their primary early customers that they have a rocket capable of doing everything that it needs, which is more than the Falcon 9 can do. And that will give a reason to buy this rocket instead of the cheaper Falcon 9. So we're looking at least 2 more launches in 2018. And there's a couple more customers lined up just without launch slots picked out.
Very awesome.
Well, they need to continue to schedule them around my committee meetings because it was very exciting.
Should send,
or
send
during
your
class.
schedule.
I'll show it.
Yeah.
I'll show it during class. Yeah, here's my Google Calendar. Yeah.
Yep. If you wouldn't mind scheduling those.
All right, Kimberly, how about we
Yes.
talk about everybody's favorite planetary system, TRAPPIST-1. What's going on there?
TRAPPIST-1, which I will say it's one of my favorite planetary systems, and I have a whole ranking system of my favorite planets. TRAPPIST is like the top 7 slots. So that, as a reminder,
Why?
well, even more so now. Well, one, it's a very close by planetary system. It has 7 planets, where 3 or 4 of them are nominally in the habitable zone, but all of them could potentially be habitable. They're all about Earth-sized. And 2 new studies have started to fill in some of the information that we didn't have before about the TRAPPIST-1 planets, and that is particularly their masses, their densities, and some of their atmospheres, which, if you listen to me speak about planets at all, I'm all about the atmospheres and what they're made of. And so these 2 new papers that talk about the composition of some of the TRAPPIST planets have showed that all of them are mostly made of rock. Yay, mostly made of rock. And some of them may have up to 5% of their total mass in water content. So mostly rocky, lots of water. And the second study was looking at some of their atmospheres using Hubble and was able to rule out one of the most inhospitable atmospheres that you can have, which is a very hydrogen-rich atmosphere, sort of like we see in our giant planets and our ice giants in our solar system, which would have made those nominally habitable planets way too hot for life. So we've ruled out some of the worst-case scenarios. Atmospheres, probably decent, and rocky compositions and lots of water. So we're sort of starting to pin down exactly how habitable these planets really are. So
how does 5% water compare to the Earth? What percent of Earth
it's
is
something
water?
like, Earth has something like 0.02% of its mass in water. So these TRAPPIST-1 planets could have up to 250 times the amount of water that Earth has in its oceans, which is an amazing amount of water. Now, there's no telling, if it's surface water in oceans, or if it's locked up in the mantle and the crust, or if it's some combination, or if it's in the we don't know. And that'll all tie into, what the atmospheres are doing and what the temperatures at the surface are really like. It's just we know the water is there, which is good.
And one of the things that was really cool that came out of this was it's not switching over. There we go. One of the really cool things that came out of this was scientists were working on making a plot showing for the TRAPPIST system versus our own solar system, this line of temperature versus the planetary density, gravity. What gets you at how bad is the gravity going to be at the surface of the world?
Yeah.
And when you look at that plot, you see Venus and Earth. Venus should be habitable, but that whole greenhouse effect kind of killed it, literally. You see that some of the TRAPPIST worlds line up and fit within this habitable set of ratios. And it's just beautiful to see everything lined up.
Yeah, in particular, planets C, D, and E are very, very close in composition and in the amount of irradiation that they're getting to what Venus and Earth are. They're remarkably similar in those 2 quantities, which are very, very important, for having an Earth-like surface. And on top of that, those are 2 of the planets where they got the atmospheric measurements on top of some other atmospheric measurements for the other planets. And so I think, in my opinion, of the TRAPPIST planets, C, D, and E are the most likely to actually be not only habitable, but hospitable.
And I finally grabbed that graphic to share. Apologies for how ineloquently I'm sharing it, everyone who's watching. I'm not Fraser. So you can see in this plot that we have the planet radius along one side, we have the mass along the other, and all the planets are lining up nicely. And there's another one that relates in temperature that I'm working to find. So stay tuned while I look for that
I
one
think
as
it's
well.
planet D, if I'm remembering my TRAPPIST planets correctly. I've spent a long time looking at these graphs going, these are so cool.
So, Kimberly, what can we hope to learn from James Webb about these planets that we haven't been able to learn from Hubble?
Right. So the thing about the Hubble measurements is that they were only able to rule out one type of atmosphere, and that was the very hydrogen-rich atmosphere, which it's a good thing to rule out, but it didn't really tell us what is there, more just what's not there. So they weren't able to get any broad absorption features from anything like water vapor in the atmosphere or carbon dioxide or methane or anything like that. Hubble couldn't tell them that. That's something that James Webb could be able to do, and likely will do within its first year of operation, as well as getting some more accurate measurements of the temperature structure of the atmospheres themselves and doing it more precisely. So it's not just, what's there, but how does that affect the temperature going from the top of the atmosphere all the way down to the surface? And that's how you really get at what it would be like to stand on that surface, whether you'd be boiling or freezing or just right.
We have Larry asking in the chat, how about red dwarf flaring? How does that factor in on all of this?
So that will sort of determine whether or not the star itself keeps blowing away, stripping away the atmospheres of these planets. So if you remember back to when we first started talking about the planets, even the outermost TRAPPIST planet falls well within the orbit of Mercury. They're very, very close to the host star, which they would have to be because it's very tiny. And so if you want to be habitable, you got to be close. But being so close, the star might be stripping off the atmosphere with all of its solar flare and solar activity. James Webb might be able to tell us more about what that solar activity is like, and will actually let us measure the atmospheres of the inner planets to see if they're still there or not. I don't believe it'll be able to tell us much about planetary magnetic fields, which would really be the sort of saving grace for those planets if they exist. Yeah. So, TRAPPIST. Yes, we are learning.
So how far is TRAPPIST away from us again?
It is only 40 light years away. So it's pretty close.
So
it's pretty close.
I saw someone asking, when will our light sail get us there?
About 10,000 years from now.
Okay, fair
I actually
answer.
did that calculation once upon a time. It's about 10,000 years.
Wow. Stay tuned for that episode of the Weekly Space Hangout featuring Robot Fraser and friends.
So I want to be a head in a jar. So my thing with exoplanet stories is always like, they use the words Earth-like. They throw that around in titles way too much.
Oh, such a
How close is it pet peeve for you too? Okay, it's not just me then. Because I'm not an exoplanet person. How close are these TRAPPIST planets to being what we could consider really habitable? I mean, habitability is a whole thing that you have to define very carefully. How close are these or any other known exoplanets really the ones we should be looking to?
So the issue there, so in my opinion, for Earth-like, you need to be the same size, the same mass, the same composition, the same atmosphere. And all of those things combined will get you very similar conditions at the surface of the planet. Essentially, if you have all the ingredients in the right place and you cook them the right way, you'll get pretty much the same product. So for the TRAPPIST planets, we have the size, we have the mass, we have a good idea of the composition, and we're starting to nail down the atmosphere. So we're getting pretty close, and this is pretty much the closest that we've ever been to actually nailing down those 4 really important parameters. And I think it's good we're going for this set of planets. We have, 7 shots to get it right, pretty much. With Proxima b, there are so many other issues to deal with, but with TRAPPIST, it's a really great target.
And Arjuan brings up a good question. Could life exist under the ice even if atmospheres have been stripped away? Is it possible that some of these TRAPPISTs that we aren't giving enough attention to may be the next Europa or Enceladus with life under the
I see this person's a TRAPPIST-G fan.
Yes.
And I would say it's totally possible. I mean, we see life all over the place here on Earth, even under the ice sheets of Antarctica and deep inside icebergs where, you know, they don't really get much air or circulation or anything like that. It's totally possible. Whether we'd ever be able to detect it, though, I would be very doubtful of that, unless we stood something on the surface and drilled down. Same thing with Europa and Enceladus and any of these other icy planets or worlds in our own solar system.
Enceladus might spit at us. It's good that way.
Enceladus might spit at us. Europa might spit at us a little bit.
Yeah, Europa spits a little.
Our solar sail needs like a really long needle to just kind of bullseye right into TRAPPIST-G.
So short answer is it's totally possible. I doubt we will ever know.
So Nicole, you're bringing us a planet this week too. Is it cooler than TRAPPIST?
It's not just a planet. It's an entire population of planets in an entirely different galaxy. Okay, so I'm usually the one that's like, blah, blah, exoplanets, I'm going to do something else. But I saw this headline, and I didn't have time to really focus on it until I was getting ready for the show. And, the headline basically being that the first time exoplanets have been discovered in another galaxy. What? So the thing we all know is that by looking for exoplanets, we've still only probed a rather small volume of the Milky Way. I made a terrible graph of it once. I'm not even going to screen share because it's so bad. Of the location of the known exoplanets and tried to scale it to the size of the galaxy. If the galaxy is like this, then like the region we've probed is like this. I mean, it's not good. But so the thought of going beyond our galaxy and talking about these exoplanets at much greater distances seemed totally bizarre to me. But it was a really interesting method that they used. And it's kind of a statistical method that these two researchers used using something called microlensing, gravitational microlensing. So here's the setup. You have a galaxy that's far away, and you have another galaxy that's even farther away. And the galaxy that's not as far away acts as a lens. It bends the light of the back galaxy around it. So this background galaxy, this quasar, has a supermassive black hole in the center. It's gobbling up gas, spitting gas out. It has this really bright disk around it. And we can see images, not reflections, but like projections of that. Distortions, thank you, of that around the galaxy that's at the middle distance. By looking at tiny, tiny fluctuations in those images, you can get a sense of the mass distribution, or the mass size distribution of stuff in that lensing galaxy, that middle galaxy. So that's the one where the exoplanets have actually been discovered. So you've got, so they had to use a computer model to compare it to their observations. And they had something like 10 years worth of X-ray observations to look at for these tiny fluctuations. And so they found that the best fit to the data was a model that not only had stars in it, which they expect to see, but for the tiniest fluctuations, it needs to have even tinier things. And so they had to have a population of something like 2,000 objects of a size between the moon and Jupiter. So 2,000 in a galaxy of however many billion stars isn't a lot, but these aren't necessarily exoplanets in orbit around their stars. In order to act as tiny little lenses on their own, they can't be close to a star. So not only are these exoplanets, they're rogue exoplanets. They're rogue, so 2,000-ish rogue exoplanets floating around in this galaxy that is causing these tiny fluctuations. So the astronomers who did the study pointed out that, never in our wildest sci-fi imaginings will we have a telescope that will actually be able to see these planets. Maybe our wildest sci-fi imaginings we could, warp there and visit them, but we're not going to see them from Earth. but they made that statistical determination. And they compared that to the determination of how many rogue planets are in our Milky Way, and it's well below the threshold, the kind of the detection limit. They think that there's something like, there can be no more than 10,000 rogue planets of this size in our galaxy, and this 2,000 is well below that. So we haven't seen an exoplanet. We haven't even glimpsed, a specific characteristics. But statistically, they've been able to model all of these rogue exoplanets in this distant galaxy, which is cool because we kind of expect other galaxies to be similar enough to us. They got the same physics going on. They, if stars make planets at the same time, then stars in other galaxies should be making planets too.
So Kimberly, I think we all believe that other galaxies have planets. Do you believe that what these people are seeing are actually evidence of planets? Planets are small, other galaxies are really, really far away.
Yeah, I don't know that I am entirely convinced. I've read this. I did actually read this paper today. And there were two parts of it that stood out to me as I'm going to narrow my eyes and look sort of askance at this little part here, which if you're watching the video feed, I am doing right now.
You're really doing it right now. Good, because I tried to read this paper and I got lost in several places. Okay. So the first, let's go.
Yeah, so the first part that I sort of am going here is something you said, Nicole, which is that they found they modeled approximately 2,000 planets, which is well below the Milky Way's estimated number of rogue planets. The thing that they did, though, is they restricted it within a very narrow bound of how many rogue planets would work. And that's just a factor of the computer simulations are so difficult to run, they had to restrict something because you can't explore the entirety of any possibility even with a supercomputer. So they had to restrict it, but I feel like they restricted it to a very narrow part. So they sort of, maybe they honed in on an answer that may work, but may not be actually the best possible answer. So I'm skeptical about that. And also, given that we don't actually know how many rogue planets in our Milky Way, it seems a little bit of a possibly cherry-picked answer in that respect. And the second thing that I'm really not convinced by is the fact that they pre-selected how many moon-sized objects there would be compared to Jupiter-sized objects, which is something that we do with stars a lot with a model called an initial mass function, how many small stars there are compared to large stars. And that's something that we know pretty well for our Milky Way.
From observations. From
observations of this is the mass, we've counted this many stars of this mass, red stars versus yellow stars
to back up on that, this one is super easy to do. Let me look at the camera, because all of the stars in an open cluster or a globular cluster will have formed out of the same cloud. And we can look and see all of these stars, count the number at this mass, count the number at this mass. They all form together.
They all form together in the same place.
There.
Yeah.
We talked about this a few weeks ago with the observations of the Large Magellanic Cloud, and there were supermassive stars that were rounding out the top of the IMF. Yeah.
So for stars, in the Milky Way, we can do this, and we can infer those sorts of things for other galaxies, because for some we can actually observe, like for large and small Magellanic Clouds, we can observe individual stars and get those from observations. But even for the Milky Way with our planets, we don't have an initial mass function for planets. We don't know how much more likely it is to form a moon compared to an Earth compared to a Jupiter. That's very much one of the biggest questions we still have in exoplanets is, given this material around this star, what are you going to get? We don't know. And they assumed that and applied that to their model. They said there's going to be X many moons compared to Earths compared to Jupiters, and let's see how many planets we need to get that. So
do they base that estimate on anything? Is that based on our solar system, or is it just kind of a good guess?
They did base it on one research paper, which I've not actually looked into. But it was one it wasn't just an arbitrary selection that they picked. It was based on previous research that I have not actually gone and looked at. But given that we don't know that too well for the planets we have detected directly, I hesitate to apply it to such a distant thing.
Now, have we found any rogue planets in our own galaxy so far?
Well, it depends on what a planet is, I think.
Have we found any rogue small bodies that are less than 80 Jupiter masses?
Yeah, we have.
Okay.
Yeah, we have.
With microlensing.
With microlensing.
Yeah.
With two of our really extensive gravitational microlensing projects from the ground, Nicole. And they've done great work, and we've discovered something like 50 or 60 planets just using gravitational microlensing. And most of them are, small rogue bodies that, that they flit past, or there's a star going past and there's a little extra blip from a planet in orbit. So I mean, it's a well-tested and well-tried technique for planets. But that doesn't necessarily give us what the true distribution of large to medium to small planets will be. And that's the part that really stuck out at me, that they assumed it, they applied it, and they fixed it in their model. It wasn't something that they let sort of roam free to try and find the best fit. It was one of those that they said, this is what we're going to say it is, and given that assumption, how many planets do you need?
So the reason they went into that, as I understand it, is because just using stellar populations didn't model all of the fluctuations that they saw. Mm-hmm. So something else was going on. So maybe their hypothesis is too narrow, but what else could cause those tiny fluctuations?
So I don't think that I'm not going to shrug off the hypothesis. I think it's totally possible that a large population of rogue planets could be causing micro fluctuations in these gravitational lens images. I think that's a totally valid hypothesis. I'm questioning the specifics of how they got to the
number and the size
planets down to the size of the moon. That's the part that I'm really skeptical about.
The way I look at it is they're looking at this giant galaxy. They're seeing all of these fluctuations that are driven strictly by individual things that are lensing light in the background. And in trying to model it, they had to make assumptions. And with stars, we know what stars do. So they used the standard distribution of stars. And then they were stuck, and they probably had limited computer time, and they couldn't run all the possible scenarios. And based on just stars, they couldn't make it work. So they knew there had to be something else doing the lensing that was free-floating. This isn't the planets, like you said. It's not the planets associated with the stars. It's rogue, small, off on their own bodies. And since they didn't have enough computer time, they're like, okay, we're going to make a guess. We're going to throw this guess in. And using this one guess, we get 2,000 moon to Jupiter sized objects. And now it's on the rest of the scientific community to build on this work, run all these future models, and see if we can get a better fit to the data by trying other distributions of rocky and gassy bodies. And so this is a starting point saying, we can't fit this with stars alone. Just like dark matter was a starting point initially of it's not stars. And now we're going to get there.
It's also not stars.
You're right. And so it's a starting point.
So are there other observations that we could make of other galaxies that might shed light on their planet populations, using a different technique that maybe we could sort of cross compare with?
Oh gosh.
Is microlensing our only game in town?
Away. Not for something that far away. I mean, I could, if you want me to envision a very, very low probability event, I would say something like we see a supernova in another galaxy, which is something that we've done. And there's a transit of a debris of some sort in front of the supernova light curve. something. This is my like completely out there probability.
Even
so
that,
the bottom line is
sizes are wrong.
This is the only game in town. Yeah. We either sort of believe this kind of method can yield us something, or we concede that we'll never know anything about the distribution of planets in other galaxies. Is that kind of the choice we're left with?
Yeah, see, Nicole, I want them to do a similar thing with a different lensed quasar and a different lensing galaxy. I would love to see that sort of calculation to see if I'm sure that there are similar 10 years of data for a different lensed quasar somewhere. Sure. And I would love to see those kinds of calculations done for another galaxy, or even, 10 more.
Well, it looks like, this one I think was published in Astrophysical Journal Letters, which is here's a short-ish paper on something cool we're going to put out quickly. So it might be like, hey, here's the first, look at the thing.
That would be really awesome.
I think further study would be a much bigger paper. And this was kind of a, hey guys, look at this. It's kind of what AppJ Letters, what we use it for.
That's also a good point. I think my official stance will be, it sounds really cool and I want to know more so that I can be convinced.
I was considering that when I first saw the headline, I was like, that's ridiculous. I went from that's ridiculous to, oh, okay, that's kind of interesting. Yeah.
All right, Pamela, you've been heroically producing the show, but you brought us a story about some baby asteroids.
So this isn't the most exciting of stories compared to everything else tonight, and it won't let me. There we go. It finally let me embiggen myself. No, go back. Sorry, I can't produce myself. Apparently, there we go. So. One of the things that I'm deeply appreciating is as we get more and more telescopes out looking in more and more parts of the sky, we keep finding more small rocks. We had ever so amazingly, Oumuamua, I think is how it was pronounced, last month or a couple of months ago, this extrasolar, I guess it was September, was longer ago than I thought, this extrasolar rock that raced through our solar system. And now we've had two little tiny asteroids that both came within 40,000 miles of the planet Earth. These are objects that are 50 to 130 feet across. They're tiny. But we're still trying to get an understanding for how many rocks the solar system is sending at us. And these could have, either one of them, been another Chelyabinsk event, another case of something coming in and either exploding above or in some part of our planet, which is thankfully mostly water. So I just love seeing that the more we look, the more we find. We are constantly dodging rocks as we orbit the sun.
So are you in favor of any of these sort of asteroid detection missions that have been put forth by NASA or by like B612 or any, you think that's a good thing that we ought to spend like a Discovery class mission doing?
I think it's worth trying. I wish that Planetary Resources was doing more on the original timeline kind of work. If we can go out and start grabbing these things and probing their composition and then just spray them white for fun while we're out there, but at a safe distance. I'm not talking Earth orbit crossing asteroids. I think it's important for us to start trying to figure out what it takes to move something that's already far away and is going to stay far away.
Yeah, it's a very good point. I mean, there are, there's one sun, there's 8 planets, there's dozens of dwarf planets, and there are hundreds, thousands, millions of these tiny little asteroids and comets and all these things that could, be very devastating for Earth, or even, just tell us more about how our solar system formed and what it was like then and what it may be happening elsewhere. The most numerous population in our solar system are these tiny objects, and we don't know much about them.
And what's
They
really
could ruin your day.
Really could. Ruin the dinosaurs' day.
What's also really amazing is just how technically difficult it's going to be to go and grab one of these suckers. The amount of gravity that you have from a rock that is measured in football fields instead of in thousands of miles, these little tiny rocks, you can't get gravitationally attracted to in a meaningful way. So you have to fly up to one and grab it and hold on. And they may be rotating in multiple axes. So this really becomes a case of grabbing the tiger by the tail, except it's an asteroid that could crash on a city, which is why you practice with one that's far away.
I have this vision of the claw machine from Toy Story grabbing an asteroid and like all the toys slipping away until one just,
We all have that one friend that's really good at those.
At
like
the claw
that's
machine?
the person. Yeah, at the claw machine, because the rest of us are terrible. There's
Uncle
always
Sam
that
needs
one
you.
person. There's always that one person. We're gonna put them driving that
If you
space.
thought that skill was not marketable, we've got a job for you.
So, I mean, we've got a couple of really cool asteroid missions, actually several cool asteroid missions that will be unfolding in the next decade. And after decades of sort of ignoring asteroids, we've finally, I think, kind of come around to the idea that asteroids are cool too. And so we have OSIRIS-REx on its way. We have Hayabusa 2 from JAXA. We have Lucy and Psyche that will launch in the early 2020s. We're finally paying attention to asteroids in the way we should have been paying attention to asteroids, as not only one of the closest astronomical bodies and the thing most likely to ruin your day, but as evidence for some of these questions, like what is the initial mass function for planets? And why does our solar system look like it does? And so not only will we answer those questions, but we might also save ourselves a splat on the face in the coming years.
It's kind of awesome. But
I love
we're
asteroids.
now hitting 1 hour into our production, and I think we're out of stories.
Yeah, I think we are. I want to remind everybody that if you're new to the show and you like what you see, we owe our very existence to the Weekly Space Hangout crew, who basically do all of the work so that we can just fumble around and try to produce the show for an hour every week. They're the ones that find some of the great guests that you would notice if you went backwards in this podcast feed or YouTube channel. And if you want to participate, you can join them over at wshcrew.space. It's absolutely free. Fun place to hang out and talk with other space enthusiasts and find the next astronaut who's going to come on our show. If you're listening to this as a podcast, please go ahead and leave us a rating and review on Google Play or on iTunes. That's really important for us to be able to demonstrate to people who matter that you guys actually listen. And so we can justify continuing to do this and spend our time on that. If you're watching us on YouTube, we'd love it if you'd subscribe, give us a thumbs up on this video. And thank you. And let's go around and sort of plug ourselves for a moment. Pamela, I see you at the moment, so let's start with you.
I am Dr. Pamela Gay. You can find me professionally at cosmoquest.org, where I invite you, yes, you, to come help us map out our solar system and beyond, to find the safe places to land that rover and the scientifically interesting places to go explore. When I am not over there, you can find me working with Fraser, who I see you in the chat, Fraser.
Hi, Fraser.
You can find me working with Fraser on Astronomy Cast, and you can also find me just being me as Starstrider on Twitter, Twitch, and sometimes even YouTube.
Nicole.
Hi, I'm Dr. Nicole Gallucci. I am professoring at St. Anselm College in New Hampshire, where I am teaching, I'm teaching planetary science this semester, and I'm teaching strength of materials, and I have an independent study student looking at life beyond Earth, and I'm always behind on a stack of grading. When I'm not professoring.
The WSH crew can help you out with that.
Oh God, no. You want to grade my strength of materials homework?
We like
there's
them.
Probably there's actually some engineers in here, I'm sure, who could do better than me. When I'm not doing that, when I am on the internet, I'm at Noisy Astronomer on the Twitters and most of the other social media places.
Kimberly.
Yes, so I am Dr. Kimberly Cartier, and that still feels very, very strange to have the doctor in front of my name, I will say. Yeah, it's been less than a year, though, so it's fun. People can always find me on Twitter at AstroKimCartier, at my very outdated website, KimberlyCartier.org, that I will update as soon as I have a free moment, and all of my professional writing on EOS.org, EOS.org. Go check it out.
And I'm Morgan Renberg. Fraser, please come back. Your job is really hard. You can find my work over at morganrenberg.com and follow me on Twitter. Thanks for joining this week, and we'll see you next week.
Bye.
We survived.